Well, thank you very much for joining me here today. This is Paul Taubman with a 9.connects. Today's webinar topic is going to be on documentation, manufacturing documentation. As we titled it, they want what documentation? Because all of us have been there at one point or another. So today we are definitely going to spend the entire hour on nothing but the documentation that is necessary to get you through fabrication and assembly. Here at 9.connect, we basically teach, coach, and consult in PCBs. Right? And each one of those terms that I just drew out there actually have a real definition to us. We're not just saying that in terms of a general concept. We actually do consult, we actually do teach, we teach training classes, and we also coach on a one-on-one basis. One of the things that's really interesting to us here at 9.connects is learning about how people learn about PCBs. And if you look at the list that we have here on the screen, there's a number of different ways to learn about PCBs. And you can take a look at it here. There's some classes in academia. You certainly can learn from your colleagues. Experience is one of the greatest of all ways of learning. EDA tools, articles, webinars, which is what we're doing here today, specifications, and books as well. But what we find more often than not is that we never really get the whole story from any one of these things. We can get very specific articles, we can get into a book that gives it from a certain perspective. If you take an EDA tool course, for example, they'll teach you always the schematic and the PCB layout editors, also the libraries as well, but they never really talk about the manufacturing aspect of it, and they certainly never really talk about the specification aspect of it either. So I think the biggest problem that we have in this PCB community is that we really don't get the whole story. So the bigger question is, what if there was a comprehensive but readable reference guide out there? Or what if there was a training that really brought all this stuff together? Well, here at 9.connects, we have pondered all these questions and we have come up with the PCB Fundamentals training. Right? So what is this training? Well, let's start off with what it is not. It is not a tools training. Yes, here at 9.connects, we are experts in Altium Designer. But this is not about teaching Altium Designer. This is a tool agnostic course. We are trying to teach the process. Who is it for? It's for everyone. If you're a new grad or if you even have a lot of experience as a PCB designer, even if you're a program manager, one of the biggest things I have found in my personal experience dealing with the PCB process is that if you don't control it, it will certainly control you. So that's why this class was made for everybody out there who is involved in this particular process, the PCB process. It's a training that shows the entire process, and we really dive into the concepts of DFM and DFT. So for those who are not necessarily familiar with those, DFM is designed for manufacturability. So it's one thing to just throw together a schematic and a PCB layout. It is another thing altogether to make sure that you put together documentation that is manufacturable, especially for the fabrication of the board and the assembly of the board. And that's what encompasses design for manufacturability. And we talk about all aspects of it because it really becomes a methodology or a philosophy that is embedded in all aspects, whether there's a specification that you're writing, the libraries you're putting together, the schematics that you're drawing, the PCB layout that you're putting together. And the same thing with DFT, design for test. So those are the two things that we're going to emphasize in our class here. What are the topics? So these are the main topics over here. The reference guides that we have has several other chapters, but these, if you really look at, are the main modules. And you'll notice really at the front, we're talking about manufacturing from the very start. We're not going to jump into the schematics and the layout. That's probably an area that you're very comfortable with. What we want to do is immediately show you what is the manufacturing process. What does it take to fab? What does it take to assemble it? What do you have to do for test? And then we jump all the way around to the other side and say, what do we need for a specification? So we'll also talk about writing specifications. Now in terms of libraries or the schematic or the PCB, we're not going to show you how to push a tool. What we're going to do is show you what is necessary so that your schematics are readable, that your symbols and your footprints are very comprehensive, and that your PCB is going to come together rather well, rather than just being this mishmash of things that you throw together and hope that it all comes together just right. Because really the PCB designer is a diplomat. You may have not even thought of it that way. But when you think about it, the PCB artist or the layout person has to integrate with a number of different other groups. For example, your mechanical engineers, got to talk to the program managers, got to talk to the purchasers, got to talk to the fab folks, got to talk to the test folks, got to talk to the assembler folks. So it's a really daunting task because you're trying to satisfy a number of different requirements coming from you at all different directions, and that's what we want to focus on. And of course, lastly, documentation generation. What is needed to get it manufactured? So we're going to talk about all the different documentation that is necessary to get you to fab, to get you to test. And by the way, there's quite a bit of things in there, and there are things that we still throw in there to this day, and you'll see this in this webinar today, that are, for example, they're archaic. We throw them in because a couple of decades ago they were very useful, but now we throw them in almost because, well, the tool just allows us to throw them in. So we want to talk about the documents and which ones are pertinent and what are we really looking for in those documents. And as a matter of fact, today in this 1-hour webinar, we're going to give you a very brief overview of those documents. All right, what are the results that you can expect? Look, you know, if you're going to take a class like this, you're going to expect some type of results, and this is what it is. You're going to come away with understanding what it takes to do better libraries, documentation to guide your project, and more importantly, less meetings and emails. You've probably been in those projects before, the death marches, where it's just emails every day, it's meetings every day. You're not making any progress going forward. Why? Because there was nothing to guide you. We'll talk about readable schematics, instant bills of materials, less respins, and of course less manual efforts in putting together all of that documentation. And quite frankly, there's quite a bit of it. So if you're interested in this class, please do take a look. Here's the web link below. It's on our site, 9.connects. And if you click on the training, you'll also be able to navigate it very easily on the top menu. So PCB or Training PCB Fundamentals. All right, let's get on with our webinar over here. As we mentioned before, the title of it is They Want What Documentation? Because I can't tell you how many times I've heard that in my career. So what are our objectives today? Number one, we're going to list all the pertinent files for fabrication, assembly, and for test. More importantly, we're going to determine where and what in the PCB process lends themselves to this particular documentation. So a lot of times we do create documentation at the very end of the PCB. What we're going to find out is that things that we had to do earlier on, especially in the libraries or even in the schematic, are going to play a big role in how easy that documentation is going to come together. And in certain cases, certain things have to be put together long before we even get to the end of it. And you'll see this very much so when we talk about assembly. All right, our objectives again continued to encourage you to understand what is being sent. Open up those files, take a look at it, see where it comes from. It's not really a mystery. Very few of these things are binary. It's really easy to open them up in text files. I encourage you to take a look at how those formats are put together. But the key thing is to stop throwing it over the wall. And I think we've done that all too often here in our industry. The designers, we design things on this side, and as far as we're concerned, the manufacturing side is this big tall wall. We throw things over it, and we hope that they can work some miracles. Now in the past, that was probably okay because everybody used FR4. You could easily throw an extra layer in there. We never worried about impedances. But today with high-speed design, especially with the issues of impedances and signal integrity, we've got to stop that process. And of course, we're also using different materials other than FR4. And as many of you may know, those materials have their own Achilles heel, and you just can't just slop together materials and hope that they're going to work. All right, let's take a look at the, let's say, 50,000-foot view of what documentation is. It does have three main purposes. Number one, to instruct a human on what needs to be made or what is being requested. And this is very important. It sounds kind of silly, sounds kind of rudimentary, but a lot of times we throw things at our fabricator or assembler just because the EDA tool will produce it for us, but we really don't know what we're throwing at them. And the big thing is to actually ask them what they need. And that's not a sign of foolishness or cowardness or meaning that, well, obviously you don't know what you're doing. It really is a statement that says, I want to help you. And trust me, they will not berate you. And the exact opposite will happen. They will embrace you with open arms and say, thank you for asking. This is why we need it, and what we need and why we need it. So please do ask what they need. And if there's one that just doesn't make any sense to you, again, have that conversation with them. Number two, to program the machinery. So much of this now is automated, especially both on the fabrication side and the assembly side. So some of these formats are going to look a little bit cryptic, but they are obviously made for machine use. And then lastly, to verify the end product against the design data. So things primarily like the Netlist. The idea is that, hey, we're going to put this thing through a fabrication process. The fabrication process actually uses a lot of chemical processes, Chemical processes are never 100% perfect, and there are things that can happen in that process. There's over 40 steps that can happen that can actually ruin the yield. So they need to verify that what they built is what you asked for. So there is a reason for adding Netlist, for example, and we'll talk more about that later on. But there's always tests going on as well. We want to verify, right, so that we know that what we're getting works and that what they're yielding is high. Let's talk about fabrication. Of course, obviously that's always the first step. So the first step, here's a number of different documents that need to be created, and we'll go through each one of these here. This is not always necessarily a complete list. There may be other things that have to be provided as well. The thing that you always have to remember in the back of your head is you want to talk to your fabricator to see what they specifically need, because a lot of it is driven again by the equipment that they have, or if you're asking for something above and beyond what they would call the norm. All right, let's take a look. The first thing we're going to talk about is manufacturing files. And manufacturing files are generally referred to as either Gerber's ODB++ or the IPC 2581. In the past, I think a lot of people call them fabrication files, and that's really a misnomer. And the reason why that's a misnomer is because there's so much information that comes from these files that actually go to the assembly folks. And here's an example that I show you here. So obviously the primary purpose is the copper information. That's where you get your copper information so that you can make the layers on each one of your boards. But there's other things that come along with these manufacturing files, such as the solder mask, which the fab needs, the solder paste, which the assembly needs, mechanical information, which both fab and assembly needs, and of course the silk screen as well, which the fab needs. So there's a number of different things that come from these fabrication files. So when people call them fab files or fabrication files, it really is a misnomer because they're used in both the fabrication side and on the assembly side. I'll make note of this as well. It's really rare to find an organization that does both fabrication and assembly. They are out there, but they're very few in number. So most of the time you're going to have to make a fabrication documentation set and an assembly documentation set as well. So just be very well aware of that you're actually probably going to deal with two different organizations. What are the formats out there? I'm going to give you the three main formats. I know that Gerber just recently created something called Gerber 2 or 2X, and I haven't spent a lot of time on that. But the fact of the matter is these are what I'll call the big three that are out there that can be produced by pretty much any EDA tool. Gerber formats have been around the longest. They were released in 1980. They were released by a company called Gerber Scientific, which specialized in equipment, photolithography equipment, specifically for the copper aspects of the fabrication process. Over time, they were bought out by a company called UCAMCO. And what's interesting about it is that though it's readily available in terms of the format and use of the Gerber format, it is actually proprietary. Secondly, there is the format called ODB++. It was released in 1995 by a company called Valor. And Valor was a CAM tool. It's still out there today as a very powerful CAM tool. It's used by many fab houses. Recently, and back in 2010, it was purchased by a company called Mentor Graphics. Now, Mentor Graphics is an EDA tool, and when they purchased Valor, they were also gunning for the ODB++ format, which is used by a lot of fabricators as well. And the ODB++ format is proprietary, and Mentor Graphics started to flex their muscles over the fact that they had ownership of this. As a result, there was an IPC committee put out together, and the IPC is an organization of fabricators and designers to try to establish standards throughout the PCB industry. So they came up with the IPC 2581. It was released in 2010. I believe in 2011 is when they were able to successfully create a board using the IPC 2581 format. It has been released by IPC. It is still owned by IPC, and it is not proprietary. And again, it was really a response to the fact that the other two fabrication file formats were proprietary. So that's the basic history of it. Well over 90% of the fabricators out there still use Gerber. There is a value to that. The Gerber files are very rudimentary. They do not contain Netlist information, unlike the ODB++ and the 2581, and that can be a benefit, especially if you are sending your Gerber files overseas to places where they do not have a respect for the IP. Or they may, and what I mean by that is they may reverse engineer it, they may make it into their own product, they may rip it off. Those are the kind of issues that you always want to think about when you're creating this stuff. Because remember, you're giving them the instructions to build your intellectual property. All right, some examples of these manufacturing files. They look a lot like what you would see in an EDA layout tool, just that each one of these things is its own separate file or a separate area within the code that's being put out by the ODB++ or the IPC 2581. So here's an example of a top layer and a bottom layer. Here's an example of a silk screen. Here's an example of the solder paste. So these are the type of layers that you can expect from the manufacturing files. In terms of presenting or style of it, here they kind of handle it in different ways. So Gerber itself has traditionally always had one file for every single layer out there. And you can see an example over here. And in fact, they kind of keep even to the old DOS days of the 3-character extension. So the first letter after the extension is always the letter G, which stands for Gerber. The second letter could represent either mechanical layer by the letter M. It could be a letter P for paste. It could be a letter T for top. It could be the letter B for bottom. It also, the last letter that you can see there could provide a little bit more information about it as well. So these are all the files that can be generated through the Gerber set. Okay. Now the ODB++ is actually a directory subset. It's basically a directory of a number of different files. And you can see over here, for example, when I created the ODB++ for this particular example, and we had to go down 3 additional layers in order to see all the different layers that were actually a part of this particular design. Now, most of the time when you deal with ODB++, you get something that's called a .tgz file. So Tango, the G is Golf, and Z is for Zulu. And that is actually a byproduct of Unix or Linux. So give a little history here. In 1995, most of the EDA tools, with the exception of really Protel, were being developed and used on Unix systems. And in Unix systems, in order to get your information out to the fabricator, you usually created a tape. And as a matter of fact, in the ASIC world, they still call the release of their information to the wafer fab developers, they call it tape out, even to this day. But that was the idea, is you put the information onto a tape. Now, in order to do that, you couldn't just put files on one at a time. You had to stream them onto the tape all at once. And if you wanted to add something else to it, you actually had to start the tape at the very beginning again and then restream it all out. So there's a feature in Unix called the tar command. And the tar command allowed you to take all the files and all the directories and basically put them into one file. And after you had this new file, it was given the extension .tar, T-A-R. Now, of course, that was a lot of information, and of course these tapes didn't have that much memory capacity to them, so you wanted to compress it. So there was another feature that we use quite often in Unix called gunzip or GNU-zip, and that was usually given a GZ designation. So you took the tar file and then you basically compressed it, and from there you got a .tgz file. So when people say that ODB++ is a .tgz file, they're really talking about the results of what you were doing to tar the thing together and to compress it together so you could get it out all at the same time in one stream to a tape that you would then send out to the fabricator, and then of course you'd also send it out to the assembler as well. Now the ODB++ format goes way beyond just layers. Okay, it also contains the netlist. It can also contain the via stackup. It can also contain the layer stackup. It can contain the bill of materials. It can contain schematic information, and it can contain library information. It is a very comprehensive format. Now, not all the EDA tools out there provide everything I just mentioned. Most of the EDA tools out there, especially Altium Designer, are only going to provide enough to get the PCB done. So for example, on the PC, if you did an ODB++ through Altium, yes, you will get the fabrication, or let's say the fabrication files, which are the copper files. You'll get your solder paste, you'll get your solder mask. These are the things you would expect any of these 3 formats to do. But in addition to that, you will also get your netlist. You will also get the via stackup. You'll also get the layer stackup as well. So that's all going to be embedded in the ODB++, but it's not going to go beyond that. All right, so that's what ODB++ is all about. Let's jump over to the IPC 2581. So if you can see this over here, the 2581 is basically HTML. And if it looks like HTML, it's because it started as HTML. And its history is kind of interesting. Where it came from was from Valor, who originally created ODB++, and prior to them basically being sold off to Mentor, they had handed the HTML version of it to the IPC for consideration. And they kind of got shelved for a while, and IPC did have another version out there, but it was not as comprehensive in terms of these manufacturing files. So when Mentor started flexing their muscles after buying Valor, there was an IPC committee formed. They basically took the old IPC standard, they took what Valor had given them, and they created the new IPC 2581. So that's the history behind it, and that's why it looks a little, or looks a lot like HTML type of coding. It's done in one file, and it's called a .cvg file. So those are the three formats that you can use. Pretty much at this point, most of the fabricators can do all three of them. Though again, check with your fabricators to see which one they prefer to work with. All right, one of the reasons why we put together these manufacturing rules, in addition to just actually getting our copper created, is we also want our fabricators to check the manufacturing rules of those of the fabrication files. Okay, and you know, you can send your boards out to these overnight organizations for less than $100, and they will create exactly what you gave them. Right, so the onus is on you to get your files correct. But in most what I'll call full service fabricators, they're going to check to make sure everything is all good to go. So what do we mean by this check? Well, number one, they want to ensure that the design can be successfully fabricated in the equipment that they have. So they want to make sure that you didn't put in things in there that are so small that they say, sorry, we just can't do this. Go talk to another fabricator who's got better tolerances than we do. But number two, even if they can do it, they want to clean up issues that may not have been caught in the PCB design checks. And I'm going to give an example here in just a moment. We call them manufacturing issues. So an example here is one that's called a spirit level board. It's actually put out by Altium Designer. It's a real board, not just an example that you find in their samples directory that they provide with the tool. Though it's been in there for over a decade, they have fabbed this board. When I worked at Altium, we used to use these boards as a part of the FPGA 3-day class that we presented. We would program the FPGA in the middle, and then you'd see the spirit level actually in action. So it's a real board. It's been fabbed. All right. What's interesting about this is that if you do have Altium Designer and you open it up and you run the DRC check, you are going to notice that there's one error. And the error that they give is that the maximum hole size has been reached. Or when I say that is that there's a couple of the mounting holes at the very end where on the sides where the hole size are bigger than what the maximum was allowed. If you change that, you're basically going to say no. It's going to say no error warnings and no rule violations. And so I did that. Now, when we bring this into a tool like CAM 350, when we run some of the checks on it, we do find that there's some issues over here. So for example, when I ran the copper slivers and I said, okay, anything that's of a 6 mil length or longer, let's flag, it actually found 197 of them. And these are the kind of things that they're looking for. All right, you can see these slivers over here could be problematic. If they delaminate during the process here, they can easily bridge something and short it out, and you're going to have some problems. So they would actually want to remove these things. So this brings up a couple of interesting thoughts. The first question you may say is, well, do I need to buy CAM 350? Well, yes and no, depending on your circumstance. Here's one thing that you may want to consider. For example, you have the source files, and it's up to you or your responsibility to have those source files. But let's imagine for a moment that you actually use two fabricators, one for prototyping and one for production. So you send these off to the prototyping folks, and they clean this up without you knowing about it. So immediately you already have a difference between your source files and what they're actually producing off of. So that's already a concern right there. But let's say everything goes successfully well, the yields are perfect, you go through and you test it, everything's great, and now you want to get this to a fabricator who can do high volume production, right? So now again, you're sending your source files out to this new fabricator assuming that your files have been verified. But they didn't really verify your files. What they verified is what the production of the prototype fabricator verified their work, not your work, right? So if this goes over to the production fabricator, are they going to detect the same thing? Are they going to use the same criteria? Are they going to even care at this point, right? Because production fabricators are about speed and they're about low cost. So it's not really about them making sure that everything's all nice, prim, and proper. So as a result, they may take your stuff, start running boards, and you find out that you have a yield issue, or that you're finding that these boards don't work, and yet the fabricated boards from the company that did your prototyping work just fine. So those are the concerns that you may want to have, is that if the fabricator is going to make changes to these, it's important for you to get those changes. Or, you own CAM 350 and you go through and clean up these things. Or even more so, a lot of times, you can actually find these in the design rules, but you have to know what to look for. And again, this goes back to the PCB Fundamentals class that we're offering, that half the problem is that people don't know what's going on in manufacturing, and if you don't know what's going on in manufacturing, how can you set the proper rules? For an example here, this is a polygon pour in Altium Designer. Could these have been removed long before this even got to fab? You betcha. This would have required you to know the properties of the polygon pour, so that these would have been removed, because you can remove necks of a certain length. Okay, so those are the different options you have, but just be aware of the fact that if they are going in, the fabricator is going in there and making changes, that's going to be problematic in terms of your version control. All right, especially if you're going to send it off later on to another fabricator. Other manufacturing checks, here's a whole bunch of them that they do. Yes, do they overlap those things that you would find in an EDA tool? Certainly they do. Again, some of them they may have that you won't find in your EDA tool. Some of them may just actually be practices that you have to make sure find their way into the properties or into the design concepts of your layout. All right, let's talk about the Netlist here. The Netlist purpose is really to use in combination of the manufacturing files for rule checking and to verify copper connectivity at the end of the fabrication. So it's something you want that Netlist really at the very beginning, when you're just trying to make sure that the files that you got for your copper make sense, that there's no continuity issues, and at the very end you want to use again these Netlist files to compare against what you actually got to make sure that there's no opens or shorts. What do these Netlists contain? Designator names, the net names, and of course the connectivity between the pins. So there's really not much to these things. They're very, very easy to read. What's very interesting about them is there's an unbelievable number of formats out there. Okay, the list I'm showing you here is specific to Altium Designer. I have to believe that both Mentor and Cadence, who've been around just as long, probably have a list of this plus more so. So if the fabricator is asking for a net list, more than likely you'll be able to produce the net list style that they're asking for. Now, when is it created? It's created at the end of the PCB layout. The layout has to be created. You may say that's kind of a weird question to ask, but what you're going to see as we go along, there's other things that may be created at the end, but they require things to be done up front in the schematic or in the libraries, or some of these things may have to be created long before you get to the end. You'll see some examples of that in a couple of minutes. Now, if you're using IPC 2581, and I do need to fix that as 2581, and ODB++, they have the embedded netlist in it. So if you provide those to the fabricator, they can extract the netlist off of it automatically. If you're providing them Gerbers, they're going to ask you for a netlist if they're going to do any type of testing whatsoever. All right, that takes us over to the layer stack up. So the layer stack up is obviously a summary of the layer stack that you're going to be put together. Now, in the past, it was really just a matter of just saying, look, these are all my copper layers. Here are the name of my copper layers, and these are the order I want them in. End of story. Okay. But now, since we're getting into high-speed design, there's a lot more information we do want to provide. For example, the copper layer names, okay, the material, the dielectric to be used, the copper weight, or what they call the thickness, and the board layer, the board and the layer thicknesses as well. These are all really important. Why is that? Because we're dealing with impedances. Okay, we're dealing with impedances, and as a matter of fact, one of the biggest things that causes a lot of problems in high-speed design is when you provide the layer stack up at the end when you are done with your PCB layout. Again, in the past you could do that. Everything was FR4. We didn't worry about impedances. But now that we're using different materials, and now that we have to deal with these crazy things called impedances, we now have to provide this at the very beginning of the PCB layout effort. And why is that? Well, just a quick review. The impedances that we have to deal with on our board are really driven by the board itself. That's what's amazing about it. It's not about really our trace width or our trace spacing, though they do play a role in that. But if you think about it, all the things that we have to look at, the trace height, the trace width, the trace to plane distance, and the dielectric constant, these four things basically determine your impedance. And many times people say, well, you can control the trace width in the rules, and that's true, but most of the time we already know what the impedance number is. We need to know what the trace width is going to be in order to get that number. So that trace width, actually, we don't have a lot of flexibility to it. But if we know this information and we provide this to the fabricator up front, we can get some rules to make sure our impedances are correct. And those are the trace width and the trace space rules. So here's a comprehensive example. This comes from our good friend Barry Onley over at ICD, and a huge expert in this type of thing here. And this is a tool that he created. We here at 9.Connect sell it, and it's a really wonderful tool because it provides a tremendous amount of information about your stack up. What is it providing? Well, in this case over here, it's also showing your via span, so I can see what my blind and varied vias are going to look like here. It's also going to give me a description of each one of these layers here, whether it's a signal, core, plane, pre-preg, even a solder mask. And this, by the way, is important. You may say, well, why do I care about that? Because the reason why you want to care about this is because this gives an indication that you know how the manufacturing process works. Again, going to the PCB Fundamentals class, one of the very first things we talk about in that class is we talk about the layer stack up, how it is done in the fabrication process. Most people don't know that in many cases it starts from the inside out, and it's done with core materials, and then over time you add your pre-pregs, and a lot of it's also driven based on the number of blind and buried vias that you have in there. Material types are really, really important as well. So as I mentioned in the past, everything used to be FR4. The problem with FR4 is that there are dielectric constants that are kind of high, and you want to get those dielectric constants down for high-speed design. Well, there's a ton of other materials that have come out as a result of that. But as I also mentioned, there's Achilles heels to all of these materials as well. So for example, some materials are really, really mushy, or they have temperature sensitivity issues, or some of them you just can only use so many layers of it because of registration issues between the different layers. Or some of them may be so hard that it really ruins a lot of drills in order to try to get through it. Or it may have a slippery surface, so the drill point, when it comes down, actually the drill itself will slip. These are real concerns. So this tool does have a whole library of material types, but what you really want to use this tool to do is to have an intelligent conversation with your fabricator to determine what materials would be best. And as a result of that, when you put this information in there, you get the right dielectric constants, you get the right, based on your copper thicknesses, you can get the characteristic impedances that you desire. So if you've got USB in there, you get the right impedances. You got Ethernet, you get the right impedances. If you're doing DDR, you got the right impedances. And really what you're going to come out with is right over here. What is the trace clearance and the trace width for each one of your layers? Because they're going to be different. Now, fortunately, these were all the same to get similar things here, but they were using definitely different types of materials in order to achieve this. So the short of it is this: if you're going to build your layer stack up on your own, so be it. But the two key things to walk away with is, number one, you got to talk to your fabricator up front. Don't wait for the end when you've already done all this stuff and you found out that you're nowhere near the impedances that are necessary. Number two, just making sure that what you've got here is going to work, right? So you got your fabricator, you want to have a conversation with your fabricator, and you want to make sure that what you're going to put together here is actually going to work. Those are the two that I'd recommend. And that's why you want to do it at the very beginning when you're starting your PCB, if not sooner. All right, the via stack up over here. So you saw in the last slide here that you can put the via stack up information here as well. You can also declare it separately. And again, one of the interesting things about this is really declaring it at the very beginning of the PCB layout. Now, this one over here is kind of interesting because this is a real board that we pulled it from. So we basically took a board that was made available from one of the Altium users. We brought it into Downstream Blueprint, instantly created this, and when I looked at it, there's actually some concern about it. So this is, again, why you want to do these things at the beginning of the PCB layout. Because over here, what we've got is that these layers for this, basically this buried via, would be done perfectly fine. But now we've got layer sharing here of these vias, and that can be a bit problematic. So what would have to happen over here by just looking at this alone is we would know that you'd have to use a micro via. So that's why this is really important to do at the beginning of the PCB layout, to make sure that these vias that you put down can be manufactured, because most EDA tools aren't going to flag it saying you can't manufacture this. Then you start throwing vias all over the place, and your fabricator takes it and says, I can't fabricate this, or yeah, I can fabricate it, you're going to have a bunch of micro vias in there, and it's going to cost more money, and you may have even reduced your reliability. The micro vias are becoming more commonly used. They've been around for like the last decade. They're getting cheaper to use, and there are still, it's a viable way of doing it. But the old-fashioned drill and plate method is a far more reliable way of doing it, and it's still far cheaper. So that's what the via layer let's just call it the via stack up is used for here. All right, the drill files. The drill files are kind of an interesting creature, because here's a perfect example of stuff that we continue to add that once upon a time made a lot of sense, but really a lot of it now is just for show. So there are three different types of files. There's the drill guide, drill plot, and there's the NC drill file. What I'm showing you over here is a perfect example of something that's there for just for show. The drill chart is extremely useful because the drill chart tells me the different sizes of drill that I need. There's no doubt about it. But this drill pattern over here is kind of a little bit of overkill. In the past, I would need something like this because if I was manually going to do this, I would have to dimension it out. Okay, and this would have been of some use, though there's two issues with this. After I put this down and we reviewed it, we realized, number one, something of this nature, if you were going to dimension it, has to be of scale. And number two, this is almost impossible to read because the symbols should not overlap each other. So if you're going to put something like this down, you certainly can't. It's really the drill chart that's the most important. So let's take a look at the two different types. We've got the, here's the guides here, and the guides can be just nothing more than strike points, which again is really useful if you're going to manually dimension this, though really no fabricator out there has got the time to do that anymore. Okay, but I guess if you're a hobbyist and you need to do it, this is one way to do it, and you can dimension those out and make sure you basically get the right XY coordinate and then drop your drill down on it to put the hole on it. Okay, is it machine loadable? More than likely it is. You can also get these from the ODB++ and the 2581. I'm just showing an example of the Gerber. Here is the drill, so that the drill plots themselves, and it's usually a combination. So what you get is, again, you get this table here. It's going to show you the number of hits. It's going to show you the finished hole sizes. There could be additional information here too, depending on the properties that you filled in. And then you also get a little symbol where each one of those things is going to be located. In this case here, they're so small they're not overlapping, which is nice. But again, for the purposes of modern day fabrication, yes, this chart is really useful. Are these other things like the plots and the guides useful? You can put them in there if that's something people want to see, but the fact of the matter is it really doesn't have a practical use because you need to put something into some machinery in order for these to be drilled. And that takes us over to the NC drill file. So NC stands for numeric control, and these drill files have been around for decades. It was made, I believe it was primarily driven. I don't know if they made it, but I think they was primarily driven by an old company called Excelon. The format is still out there, and you can easily create this in any major EDA tool. And when you look at these files, they're kind of neat. So here, for example, was, again, that spirit level that we saw a couple of times before in this presentation. There was actually two files that came from it. One of them was for round holes, and the other one was for slotted holes. Now, it is a little cryptic, but you have to go back a couple of decades ago when CPU speeds were not all that fast, and the memory itself was not all that, let's say there wasn't a lot of memory to work with. And what's really neat about this is that they had to be a little bit cryptic about things, but at the same time they also had to be very efficient about things too. A perfect example of that is if you take a look over here where my cursor is located, you'll see that there's a Y value missing. Now, that makes actually perfect sense. What they're saying here is that the last Y value, this Y011063, okay, is the same Y value for the next X value below it, for the next coordinate. So first and foremost, why would I want to rewrite that same register again? Because that takes a write cycle, and again, we're not talking about things that are super fast here. So let's not waste the write cycle on that. It's already in there. Secondly, let's not waste the memory space of putting that value in again. So that's the thinking that they were using back then. Now again, of course, it's a little bit cryptic, and you got to see the rest of this here. So if you're interested in seeing how this thing comes together, you can easily look on this website here. It was a web archives, and they show you where to find it. If you do a Google search on NC drill file format, you'll find it very, very easily. But again, these are the kind of things you want to take a look at to generally understand what is being created from these, right? And just kind of a neat thing to take a look at. But when it comes to the drill files, that's what you want to provide. This works out very well. The drill chart works out very well. You can add those drill guides and drill plot files. They're not really value added other than just eye candy. Okay, let's go over to our solder mask over here. So what's the purpose of the solder mask? It's really to cover the copper to keep it away from the environment. The other term that you can always think of is we're tenting the copper, because copper likes to react with the air. It does over time. So when we take a look at this example that I've provided here, I've actually combined together 3 different layers. So the pink, anything in pink is basically the outline of the board, so that was a mechanical layer. You've also got your top green over here, which I normally would see it as red, especially if you're using Altium Designer. I just made it a lime green, just provide some contrast to it. That lime green means any of the area underneath is going to be basically tented. It's not going to be exposed. Any of the dark blue areas are going to be those areas that will be exposed, so that you can put down solder paste and attach your components. So plain and simple enough. Anytime you place down a component, most EDA tools, I got to believe almost every EDA tool does this automatically. When you place down a pad, you don't worry about the solder paste and the solder mask. They usually automatically provide those dimensions for you just as you're placing down those pads. However, that takes us to the next point, and that's test points. And test points are really, really important. But the reason why the test points are very closely related to the solder mask is that test points have to be declared by the designer. Okay, so in order for test points to show up over here, you have to basically tell where there needs to be openings in the solder mask. And there's 2 ways to do that. Either you do it by adding you create a test point component. That's what they did here. They probably have a footprint and a symbol that's called a test point, and they place those down, and they don't have to worry about it because there'll be a solder mask opening, and there'll probably even be a solder paste there that they need to turn off. Okay, but nevertheless, they can have a component, or if it's a via that you're putting down, or you have a via down there and you want to basically make it available so you can probe it, you have to declare it by either being a test point, or you got to unmask it in its properties. Okay. I can't emphasize enough, this is again another perfect example of DFT design for test. Yes, it is. You have to consider it for fab and assembly. You may say, well, in the fabrication process, when everything's done, I got a bunch of open pads over here anyways. Can't I just put my flying probes on that? And the answer is sure. That's what they're probably going to do anyway. But you got to think about assembly, and you got to think about prototype testing afterwards when you got a ton of components on here. And the last thing that you want to do is put a flying probe on top of a lead, because you'll damage it, especially with the leads that they make today. They're so small, you almost breathe on them and they get bent out of place. So you got to keep in mind that there's got to be openings up for test probes in other areas other than just the pads where you're going to place the components. So that's why the test points are really important. Most of the EDA tools out there are going to have ways of determining what are going to be the test points. So even if you just make a bunch of openings over here, you got to know where those test points are, so you can basically pull together where your test points are in addition to your XY coordinates. Okay. Mechanical is always really important too. Interestingly enough, what we're looking at over here is something that's actually very human readable. This is not something you would even really put into the machine. Okay, so you got to be careful about the mechanical stuff, because some of it is for the machine and some of it's for human readability. If you throw everything together as one, now you're going to actually put the onus onto the fabricator to decide which things that they need to do, and either they're going to have to redraw it again, or they're going to have to strip out information here, and you're just adding editing work to it. But what should it contain? It should contain the board outline, the cutouts, the mounting holes, etc. And where should it be drawn? Obviously, this is something you put on the mechanical layers within the EDA tools. In terms of the formats, you can produce it as one of the fabrication files, or they may even ask for a DXF DWG file. And again, most major EDA tools can oblige by creating this particular file. What I want to give you over here is an example. On the left side, this is a really great example of a board that has been, that's really for human readability purposes. Whereas on the right side over here, it may look simple and plain, but this is extremely useful for the fabricator, because all you did was just simply provide the board outline. Okay, so they know where to route. And if there was other areas where they need a route, you could draw those in there too, and they could basically feed this into a router, okay, and make sure that those things got routed out accordingly. So that's what the difference is. When you're thinking about mechanical layers, yeah, this stuff is great because it shows exactly what's going on. More than likely, you're going to get this type of thing from your mechanical folks. However, again, you want to be able to separate what is really human readable versus what will work best for the machinery. Okay. Fabrication notes. Now there's a bunch of fabrication notes here. There's only one I'll probably mention that I think is a really good example of issues that you find. The reason why fabrication notes are really, really important is because they collect all of what we call the need to knows that are not embedded in all the other documentation. One of the biggest problems I have seen, both not only in the PCB process, but even in the ASIC processes, where the process they use to make chips, is that a lot of times, especially in large organizations, you have silos, and each group is its own specialty. So you send something to the schematic group, and the schematic group says, okay, I've got the specification here, I'm going to draw this thing up, and now I'm going to hand over to the PCB guys. And the PCB guys do their work and say, fine, I'm going to hand it over to purchasing. Purchasing does their things, and you hand it over to fabrication. All right? And what happens more often than not is in some of these silos, you only know your area. You have a lot of depth, but you don't have a lot of breadth. And as a result, information that you think would be pertinent that should be given down the road doesn't find its way down the road. And so that's why these fabrication notes are really, really important. As a matter of fact, one of the things I'd recommend is that with your projects, you have a file called a run card. Now, if you ever worked on a manufacturing floor where there's a number of stages to do, and assuming it's not just one line of automation, but there's a number of different pieces of, let's say, equipment out there, and each one of these things have to find their way to different pieces of equipment, and there's a human intervention of you taking it from one stage to another. We had a run card, and on that run card, it not only told us what were the stages that it had to go through, it also showed the sign-off, and it also showed where the next process was and who did the sign-off. Okay? And I highly recommend that same concept when it comes to fabrication notes, so that by the time you get here, all of that information propagated down, and you can provide it in basically a list format. Okay? And here are the number of things that you can see here that are really important. To me, the biggest one that I think is hidden and becomes very problematic is the concept of VM pad. And a VM pad can be easily just levied upon an entire design by nothing more than a footprint. So a VM pad, basically, instead of doing a dog bone where you've got your pad for your ball grid array, and then you have a little piece of trace and it goes down to a via. Instead, you put the via directly underneath the ball. Well, if that's not called out over here, that's great. You might fab this board out. When you go to assembly, that BGA is not going to attach itself, because basically all the solder which that ball is made out of is going to just wick right through that hole. Okay, so, and that information has to be provided to the fabricator, saying, look, if I've got a via and pad, you need to know which holes it is. So this is a collection of those things that just are not going to find their way into any of the other documentation. They're really, really critical. So that's the point I'm going to drive home with that. Let's get on over to assembly here. So that's the next stage. Now, think of this for a moment. When you're building or fabricating a board, you're building your own component. Right? We're taking raw materials, we're putting them together, and we are building a component. But in assembly, we're assembling a puzzle, and we're putting together pieces that come from all over the place, and we had no control over their manufacturing tolerances. They gave us information as to what we should expect, but we didn't make it. Okay? We're just gluing it all together, and we're hoping that it'll glue together just fine. That's really what it comes to. And you can jokingly call this the boss level. So if you do any type of video gaming out there, you know about the boss level. That's the big grand finale. You go up against the boss of the entire game, the bad guy, and if you win, you win the game. And if you lose, well, then you get knocked back maybe a level. Well, in the assembly world, if you lose this, you're going to get pushed back to level 1. Because if a part is going end of life, or you got the footprint wrong, you're going to have to fix something in the library. You might have to fix something in the schematic if it was an end-of-life part and you're replacing it. You will have to fix the PCB, and hopefully it won't be a major fix. Now, if it was a BGA, let's say it was like a 700-pin BGA, and you found out it just went end-of-life, and now you've got to basically take this thing out and replace it, that's going to tear up most of your board. Okay, so it depends on which component is going to be the one, or components that are problematic. You're going to have to redo the manufacturing documentation. You're going to have to refab the board, and you're going to have to possibly continue, depending on how far you got into assembly and test. All right, you may have to do some addition. You're going to have to basically redo that stuff as well. So what's the time penalty? Well, at least 2 weeks. What's the monetary penalty? It's going to be at least $10,000, because you've already paid your fab folks to do the boards, and then also your engineering labor is a part of that as well. Okay, so just keep that in mind. What do you need for assembly? Well, here's a list of things, and so we'll take a look at them here. So the assembly file itself, this is another example of a file that had a lot of purpose to it many years ago. It was kind of become a little bit arcane, but it's still very useful to provide as a visual. So in the past, when things were done manually, what you would do is you would basically print one of these things off, and you'd lay all your components on it, and then as you were going along, you'd pull off the component and you knew where you to put it. So at the end of the day, you knew which components still needed to be put on and which one had already been put on. But now that they're using pick and place machines over here, really the general purpose of this is to really provide a map of all the components so that whoever's programming the pick and place machine gets a feel for it. Okay. Where does it come from? Well, it's a manufacturing file, so it's treated as like a mechanical layer. It's created at the end of the PCB design as we would expect. But again, here we go. Here are the catches. This has to be built into the footprint. So if you didn't put this on that mechanical layer for that particular footprint, it's not going to show up. And to draw this thing later on is quite a hassle. So it's a part of the library. And if all your library parts have this, just by you placing it down, it's going to put this whole thing together. So here's the top, here's the bottom. Right? It can be put together very easily if the work is done in the footprints. Now, what about the courtyards? The courtyards are an interesting creature. They're primarily actually for the PCB side of things. And for the PCB side of things, it's when you're doing placement. Now, most people, if they're using Altium Designer, they may be able to use the 3D bodies to do this, but there's a concern about that. Why is that? Because one of the things that the courtyard does, it's not just the size of the component. It's actually larger than the component. It's the spacing that you want for that component. Now, for most components, it's probably just a little extra spacing so that obviously the components are on top of each other. They're not going to short each other, that you can get your pick and place material, your equipment in there. That's fine. However, when it comes to, let's say, you're trying to, let's say egresses for connectors. Okay, so when I say egresses for connectors, I'm talking about, can you get your fingers in there? Right? Can this thing latch and unlatch easily, or is it smacking against components? Or if you're going to do rework, do you have to tear out a whole bunch of components around it so that you can basically get a heat shroud around the large BGA you want to pull out? Okay, so these are the things that you need to take consideration, especially if you've got connectors, especially if you're trying to do heatsink. And another one that comes to mind is also test as well. If you need to get probes in there, right, you want to make it as easy as possible to get your probes in there. So that's what the Courtyard file does. And really, when you're doing placement of the components on the PCB layout, the general idea of it is that you've drawn them large enough so that they do have the necessary space. And as long as these lines aren't crossing each other, then that particular courtyard is probably safe. Okay, that's the idea behind it. So again, for the assembly, it's just kind of nice for them to know where things are, and they can validate the fact that, hey, yeah, you can put these components on there. For those people who do have 3D capabilities, you want to be careful of those, because the 3D capabilities, and we've talked about this if anybody's interested, a webinar we did a couple of months ago on 3D for the EE, right? And it was for those designers who have to do 3D capabilities within, for example, Altium Designer, and they don't have a mechanical fellow around to do this type of thing. So now they're on the hook to get the mechanical stuff to work. And in Altium Designer, when you do a component clearance check, you can either do it based off of, for example, the component itself, the component body that you placed in the 3D, or you can do it based on the courtyard. Well, one of the dangers of just doing the component body is that if it was a connector and it needed an egress, the rule would not take into account the egress. So therefore, there's ways to trick it so that you can use the courtyard as well. But you can see where the courtyard still has its value even in a 3D world. Okay. Like everything else we talked about is created at the end of the design. It is a manufacturing file, treated as a mechanical layer. Again, you've got to build this into the footprints if you want them. So that's the idea behind the courtyard. Bill of materials, I think this has got to be the bane of every single project. This is the one that causes more grief and aggravation than anything else, because if this is not 100%, you've got problems. I always think of it like from the point of view of a principal. Principal has so many students at the school. At the end of the day, every one of those kids better make it home, because they don't, investigations and press is going to be out there to really harangue that principal as to why that one kid didn't make it home, and no one's going to take the excuse of, well, we got 99% of them home. right? Everybody wants 100%, and that's the exact same thing with the bill of materials. You can't have 99%. You got to have 100%. So what is it? It's not just a list of components. It's also the purchasing requirements as well. So for example, the manufacturer's name, manufacturer's part number, the quantities that you need, possibly the vendor that you know has it, right? Life cycle status, those are descriptions. We've talked about those at great length in other webinars here, but that's what you've got over here. What's I think happens more often than not is that people create this way too late in the PCB process. It has to be created at the end of the schematic design, right? And more importantly, it's got to be designed into your symbols. So whereas in these other files that we talked about here, like the assembly file and the Courtyard, you had to make sure that they were built into your footprints. The bill of material information needs to be set up to be built into your symbols, so that when you place down a part, your bill of materials comes together. Now, why do we want to generate these right after the schematic design? Because somebody, and hopefully you've got somebody who can do this for you, has to check things like life cycle status, the quantities available, lead times if the quantities are not available, your trade compliances such as row, Haas, reach, and so on and so forth, and if there's possibly any ITAR issues with it. So that's what the purchaser is going to have to do. Now, you may find out that that 700 pin BGA of yours doesn't fly, okay, and you'll be ripping mad about it, but it's far better for you to find out during the PCB layout process than to find out in the assembly, right? Because now everybody's got eyes on it, now everybody's mad about it, as opposed to something that you can fix before a lot of money is spent in fabrication and assembly. Okay. Solder paste files are probably one of the easiest ones out of all these because, quite frankly, they just get put together as things are going along. So, you know, it is a manufacturing file. Again, it's considered to be a special layer, and it's created at the end of the PCB design. Probably the only catch over here is that if you are going to use test points, you probably want to make sure that you tent it for solder paste so that you don't put a glob of solder on your test points, but that's probably not a big issue. So there it is, the solder paste file. The pick and place file. So this is one that most major EDA tools are going to be able to create as well. It's basically a listing of XY coordinates as to where the pick and place machinery is supposed to pick it up. So it is created at the end of the PCB design. However, again, we go back to our footprints. The footprints really need to be centered on grid, and there ought to be a common orientation as well. And as a matter of fact, there is an IPC standard, it's called the 7351, that calls out how to handle these type of things in your footprint library. There's also another IPC spec as well that deals specifically with the pick and place machinery. However, it's probably one that you don't have to worry yourself with. The key thing is just really make sure that your footprints are on grid and that you're following a common orientation. 3D, if your tool has the capability to do it, by all means use it. You know, it's kind of like, for example, if you buy that 1,000 piece puzzle, well, what's the first thing you're going to do once you get that puzzle? You're going to start working that puzzle by looking at what's on the, basically what are you looking at on the cover or the lid of that particular puzzle box, right? And that's what this is providing here as well. It's a human understanding across all disciplines. And what I mean by across all disciplines, again, there's a lot of people involved in this. So it lets the fabricator know what the board's going to look like. It lets the assembler know what the board's going to look like. It lets the test people know what the board's going to look like, the systems folks, the mechanical folks, the marketing folks, the program management folks, the upper management folks, your customers, right? So it has a great purpose. It's just a wonderful thing for human visibility. Created at the end of the PCB design, but like everything else we've seen here, it's one of those things you've got to do when you're putting together the footprint. Now, in other tools, it may be during the design itself, but they're not going to instantly come out there, meaning the 3D models aren't going to instantly pop up. You usually have to import something in like a step file in order for the footprint to have a real representation. Okay. Lastly, we also talk about the assembly notes. These are, again, a collection of need-to-knows, not embedded in other documentation. I already went through that spiel for fabrication. Assembly is no different here. The one thing that I guess maybe I'll mention about assembly is that a lot of times you want to put down any manual assembly operations, things that go above and beyond what you would thought that they needed to do. So if there's an order of component placement, because there could be some issues, you may want to place those down. If there's special attachments of the components for height purposes, like for example, maybe you've got a through-hole resistor, but you don't want it to be flush against the board itself. You actually want it to maybe have like a 1/2 inch off the board in order to, like, for heat dissipation, or you've got a component nearby underneath it that can easily reside underneath it. Those are the kind of things that you want to put in there if they go above and beyond, or there's any type of exception to the general assembly process. All right, let's talk about test here for a couple of minutes. So test is kind of one of these mushy things because we know what we get from fabrication, we know what we get from assembly, but then test is one of those things that we've done all throughout the PCB process, or at least things we should have thought about during the PCB process. So for example, within the EDA tool itself, if we were doing, let's say, some analog or power stuff, we probably did some type of SPICE simulation with it. Or in the PCB tool, we were doing our DRC check, design rule checks, when we were putting the stuff together. In fabrication, there's optical inspection. There's also bare board testing. We referred to that about the Netlist, right? We talked about the CAM tools. So those are the type of things that are going on in fabrication testing. There's also the flying probes that are going on to make sure that the continuity is fine. Assembly is the same thing, right? They've got the same kind of thing going on as fabrication does. They've got the electrical tests as well that they could possibly do at the component level. So if you want them to exercise functionality, you would have to give them a vector set of data so that they could properly exercise if you want them to do it. And then lastly, there's just an overall functional testing, what I'll call prototype testing. So the next commentary I'm going to bring forth here is really specific to prototype testing. Okay, all the other files we talked about could assist with these other things here, but now we're going to talk specifically about prototype testing. Now, again, we're going to talk about the boss level. So just when you thought you got through assembly, you're not out of the woods yet, because if you fail at the test, the prototype testing level, again, you're back to level 1, and this time there's even more penalty in terms of time and monetary penalty as well, because at this point you've already gone through the fab process, right, and they expect their money, and you've gone through the assembly process and they expect their money, and you've already paid for a bill of materials as well. So there's a lot of money at stake at this point in time, because hopefully all of this works and you don't find any major flaws in the design. What is needed? Well, there's really 3 things that are needed at this point in time. You need to have your schematics, your layouts, and your specifications. So let's take a look at that for a few moments. So when we talk about the schematics tell a story in symbolic form. That is really the purpose of it. In our PCB Fundamentals class, we go into a lot more detail about what that story is, or how we want to tell that story. Okay. Our recommendations, it's really more about recommendations. If you're dealing with outside test agencies, and maybe they're in other countries, just provide the PDFs. They need to know where things are, but if there's any opportunity for any reverse engineering going on, it becomes a deterrent if they just have the PDFs. Why is that? Because if you give me a 20-page schematic that looks something like this, okay, and I want to rip it off, I'm going to have to put this into the, I'll have to basically put it into my schematic editor, and that will take me a long time to do. Kind of reminds me of the old days when I was in college. They always threw these stacks of, they were basically catalogs of term papers that you could order, right? And of course you shouldn't have done that to begin with, right? Because that was basically plagiarism. But if you did do it, you still had to take what they gave you and you had to type it up on your own, right? So you still had to put an effort into it to plagiarize it. Whereas if you give them the source files, right, now it just becomes a copy and paste deal. In fact, you've done all the work for them. Okay. Now, if you're working in-house or you're working with somebody who does have an NDA and they are reputable, you do want to give them the source files because it allows for much easier navigation. And in fact, in Altium Designer, one of its most powerful features is the ability to find something. You'll say, hey, I want to know where C1 is on this board that's got 1,000 parts, and Altium can instantly show you where it is on the schematic and on the PCB. And I got to believe Mentor and Cadence have the same thing as well. So there's definitely an advantage if you can provide the source and you trust those people who are going to use it. As for sheet size, we recommend the largest that can be practically printed. So if you actually, everybody in the office has plotters, great, build it to a C-size sheet or an E-size sheet, D-size sheet. All right, if everybody just has those business printers where they can only go B-size, so be it, keep it to B-size. So that's what we recommend with the schematics. PCB layout, really the exact same thing. The only difference is you're talking about a physical structure, and obviously you'd want to print out each, you'd want to probably print out the assembly layer or print out something that shows where the maybe the top top copper is if you're trying to get into it. In terms of, again, for the outsiders, you may want to provide them something in a PDF format. As to how you provide it to them, that's going to be up to you. But the in-house, again, you want to provide the source so they can quickly navigate around to it. Okay. And lastly is the specifications. I think all too often one of the biggest problems I have seen with every design out there is specifications or lack thereof. And I can tell you that when I worked in defense, I probably worked on I'd say about a dozen projects in a 4-year period of time. And someone asked me during that period of time, they asked me like what projects I liked and which ones I didn't like. And I had to think long and hard about it because everybody always thinks about the manager and whether the manager was good or bad. But I found that it really wasn't about the manager. It was really about whether or not the manager believed in specifications. Because the projects that had specifications where we sat down and we really wrote out a specification went as smooth as glass. And anything that we ad hoc was always just a torrent of emails and meetings. And we never got anywhere with it, and we generally call those things death marches. So what are the specifications trying to do? They're telling us what needs to be tested. Test what it was built to and how it needs to be tested. So if you write a good requirement, okay, that requirement can be verified through one of these 5 methods. Okay, so if you write a requirement, it can be verified. Well, the requirement says it has to be blue. Okay, it's blue. The requirement says that resistor is supposed to be 10K. That's fine. The requirement says the speed of this thing is supposed to be X number of megahertz. Fine, we tested that. These are all testable things. Okay, now I'm grossly over-exaggerating some of these things, but that's the idea behind it. So your specifications say this is what it's supposed to do, so when it's time for test, they know exactly what to test. And when you don't have a specification, then it's an all ad hoc thing, and even worse, things that should have been tested don't get tested, and then you find out about them later on when they're out in the field. And that's where it gets really expensive to investigate. All right, so there's a lot more to say about all of these things and very little time to say it in. So we really want to push this concept of the PCB Fundamentals class to you. We go into a lot more detail. It's going to be a lot less rushed, right? I'm trying to keep everything here to an hour to keep not only your interest, but know the fact that you've got work to do as well here. But that's what this class is trying to provide: far more information, not to be in a rushed environment. Again, what you're going to get, all of these good things. But I wanted to add this last thing because when I was reviewing this with my colleague, he was very correct. When you do it right, the end is truly the end. It doesn't come back to haunt you or bite you. If you're interested in this class for our PCB Fundamentals, there it is right there. We're at 9.connects. Just to click on the training tab, or you can basically copy this link here. And by the way, do save the date. Our very first inaugural class of this is August 16th through the 18th in San Diego, California. Well, thank you very much for your time, and we hope that this was informative. And please join us if you're interested in our other webinars. There again too at 9.connects, you can sign up for them. We do them once a month, usually on the last Wednesday of the month, and it's always on a topic that's related to the PCB design process. So again, thank you very much and enjoy your day.